This is a really bad idea. The last time I attempted to do anything related to wave function collapse, it took me, 9 to 10 hours. Wave function collapse, the overlapping model. It's been 2 years since I released my first wave function collapse video, and about 6 months since I recorded the video that you're watching right now. It'll be a little different. I'm gonna be popping in throughout to offer a little bit of commentary where things went wrong, and hopefully that'll make it a bit more clear for you to watch. Don't worry, there's a final code example at the end that does work, even though while you're watching it, you're not gonna really believe that I'm gonna get there. Enjoy. And I often do this where I talk about how I'm going to follow up on a video with a part 2, part 3, part 4, Rubik's Cube solver, for example, and then I never do. But wave function collapse, today is the day. Let's collapse some wave, let's function, let's wave, let's surf and collapse waves, functions. First, I'm really sorry about this, but if you'll indulge me for just about 30 seconds, the Nature of Code book is coming out on September 3rd. I know, this was recorded so long ago. It's old news. The book is out now. You can pre-order it, or depending on when you're watching this video, just order it right now. Here's the table of contents. If you like the coding train, if you are interested in the kind of stuff I do on this channel, my hope is that you'll like the book. I would love it if you considered getting it, but you don't have to buy it. The whole thing is online, Creative Commons license at natureofcode.com. You can also just read it there on the website. Okay, what is the wave function collapse algorithm? I spent a fair amount of time explaining and giving some background and context about the algorithm in the previous video, so I won't go through all of that again, but let me just add a couple pieces of context. First, since I released that video, I learned about the wonderful work of Paul Merrill and the model synthesis paper that he published, I think in 2007. I encourage you, as your background reading, to take a look at Paul Merrill's work on model synthesis as well. The two main resources I'm using for this video are the GitHub repo for the 2016 implementation of wave function collapse from Maxim Gubben. Another resource I followed closely, so closely that I printed it out and I spent a lot of time with it, is from gridbugs.com, 2019 post called Procedural Generation with Wave Function Collapse. One of the most common applications of wave function collapse is procedural generation for games, whether it's a 2D map, a 3D world, and in both of those scenarios, there is typically a pre-made, pre-designed set of tiles with pre-defined adjacencies, which tiles, whether in 2D or 3D, are allowed to be placed next to each other. This is what I explored in depth in the previous video. The thing that makes this next step, what I'm going to explore in this video, the overlapping model, so special is that there are no predefined tiles. All you need is a source image. The algorithm looks at that source image and makes tiles from it, analyzes the pixels, look at how pixels are appearing next to each other in a source image, and recreates a new image in that style. I know that many of you are interested in generative patterns in algorithmic art, and the overlapping model, I think, is a key to unlock so many possibilities in abstract, generative, computational design, art, etc. And if I could somehow make it to the end of this video and hand over an example with some reasonably competent explanation of how it works, I'm really excited to see what you, the viewers, make with it. Before I can even get to the actual collapsing of the wave function, what I need to start to do is look at how do I take a source image and extract a collection of tiles from that image. The image that I'm going to start with is a very small, low resolution 9 by 9 pixel image. This image is one of the sample ones provided on the Wave Function Collapse GitHub repo, and it's called city.png. I'm going to make the choice to have my tiles that I'm extracting from this image be 3 by 3. The first thing that I want to do code-wise is simply iterate over every 3 by 3 section of this image. Here's one, here's another, Here's another. So I need to have a nested loop where I'm starting from pixel 0, 0. I'm extracting a smaller image and I'm sliding it continuously over the image, across and down. Just wanted to pop in and note that there are only 49 tiles right there. And later you're going to see the total number of tiles is 81. That's because the image is 9 by 9 pixels, 81 pixels, but I stopped getting tiles 3 pixels from the edge, so I didn't go off the edge. 7 by 7, 49. Later, I'm going to deal with that a different way so that I have the full 81 tiles. But let's go write the code. Here's my blank P5.js sketch. I've got 4 sample images. Let's start with city.png. Normally, to draw an image to the canvas, I would just say image, 0, 0. That image is really small. It's going to be difficult for us to see, and I'm going to have to do a lot of work talking about the individual pixels of the image. So I'm going to actually write my own function that receives an image and draws it at a particular width and height based on the pixel values. This is, by the way, what the image looks like blown up, but you can see that the canvas is interpolating the colors as it enlarges the image. So I'm going to write my own function called renderTile, which receives an image, an X and Y position, a width and height, and then draws the individual pixels. Right now, I've just hard-coded the number 3 in there. I might need to rethink that later, but I think that will do. I realize I put a width and height. Everything's going to be a square in this example, so I'm just going to keep just the width and draw it as a square. And this code loads the pixels, loops through each one, and draws them individually at a larger size. So I made a mistake here. I'm anticipating how I'm going to want to draw the tiles, which will be 3 by 3 tiles. But actually, just to look at this image, it should be 9 by 9. So let's make this function more generic. There we go. This is what that image looks like blown up. I'm anticipating that in this project, I'm going to have a lot of functions like this that are essentially utility functions. I'm going to create a file to store all those functions. I'll call it util.js. Including it in index.html as well. While I'm here, let me make a file called tile.js because in addition to extracting the pixel data for each tile, I'm going to want to have a tile object that can keep track of additional information. So when it starts, the tile will just be a small image, 3 by 3 pixels. And let's make an array of tiles. And why not write a function in my utility file to extract all of those tiles? Load the pixels of the image, same nested loop. The tile image is going to be a new image that is 3 by 3. What I need to do here is, step 1 is to copy the top left 3 by 3 tile from the larger source image into my new smaller 3 by 3 image. There's actually a P5.js function that'll do this for me. Now I'm forgetting the arguments here. Let's go look at the reference. Copy from a source image, XY width height, to a destination image, XY width height. I'm really going to need to put that number 3 into a variable. So now in setup, the tiles array is the result of extracting all the tiles from that source image. And I forgot to include tile.js. I no longer need to initialize tiles as an empty array because it's going to be created in the extract tiles function. Let's take a look at all of these tiles now. Okay, something went wrong. Oh, I need to render the image, which is tiles index 0.image. No. Oops, I forgot to return the array at the end of the extract tiles function. There we go. That is the first tile. Okay. They all seem to only have white pixels. So what have I done wrong here? Oh, I need to make a new image for every tile. I made the image in the outside of the loop, which isn't right. There we go. That's tile 4, 0, well, 5, but 0, index 4, 0, 1, 2, 3. Okay, great. You can see how I am going through and chopping the image up. Let's actually look at all of them. I think that will be helpful just for debugging purposes. Hold on. I need some variables that are going to keep track of a variety of different things. For example, what is the size of an individual pixel in my system? Well, ultimately, I'm going to want to think of what I'm rendering. What do we have? We have the source image, which is 9 by 9. I have a tile, which is 3 by 3. Where I'm going with all of this is I have my P5 canvas, which is currently 400 by 400 pixels. I would like to create a new image based on the style of my original image. And I'm going to have a variable, I'll call it dim for dimension, that will keep track of the total number of columns and rows since I'm working with a square. Of course, it could be a rectangle, but let's keep things simple. So for example, if I were to set that variable to 10, that means the width and height of every pixel is going to be 40 by 40 because I'm going to have a 10 by 10 output. Ultimately, I want to make this much higher, but let's just start with that because it'll make things easier to see. I take that back. Let's actually start with 40 by 40 so our pixels are 10 by 10. I think that'll be nicer. So I now have a dimension of 40. The width of every single pixel in the variable w here is the width of the canvas divided by the dimensions. And that way, what I can do is set this x value to, just for right now, width times 3. I times width times 3. And I would actually like to see all of the tiles. So let me create a variable called x, a variable called y, x comma y. We're going to increase x by 3 times the width of each pixel. And then if x is greater than width, then set it back to 0 and increase y by 3 times the width of each pixel. See, this is 81 tiles. Now, if I had just thought about this when I recorded this video originally, I would have visualized them in a 9 by 9 grid, which I think would have made a lot more sense. And let's go back to how I'm drawing these tiles. I'm going to say no stroke. Let me put a boundary around it to make it a bit more clear. So this is now all of the 3 by 3 tiles. Let's draw the larger image at the bottom just to confirm that what we're doing looks right. Okay, I'm gonna zoom in here so I can see and make sure it all makes sense. Look at how each tile drawn on top matches each 3 by 3 matrix of pixels from the 9 by 9 source image. Unfortunately, while this is really good, I need to improve this a little bit. And I think I actually have a mistake here because as I am going through each 3 by 3 matrix of pixels, when I get to the end, I have this matrix of pixels, but then I have this matrix of pixels, and I go off the edge, I'm not getting any colors there. So one approach, which is the standard approach here, would be to use wraparound. So at the end here, go and grab these beginning pixels. And you can see that there in these final tiles, how those aren't actually legitimate tiles from the source image. So let's actually change from using the P5 copy function to write my own function. Copy tile, and I want to copy from a source image from ij 3 by 3 to a destination image 0033. So this means I'm going to write my own copy tile function, and it needs a source, sx, sy, width, and you know what? Everything's going to be a square, so I'm going to keep things simple. And also, I know the destination is always going to be the full image, so I can just say the source image from pixel x, y with a certain width to the square to a destination image. Source load pixels. I'm probably later not going to need to call load pixels everywhere all the time. And in fact, that could be slowing things down, but I'm just going to leave it for right now. Now I have a nested loop to go through all of the pixels. So the index from the source image is source x plus I times source y plus j times w, and that whole thing times 4. So one of the prerequisites for watching this video is knowing about how the pixel array works. The pixel array has 4 elements for every single pixel: a red, a green, a blue, and an alpha value, and it's a one-dimensional array. I have this muscle memory now to kind of go from an X and Y position in an image to the proper spot in this larger one-dimensional array where I can find the RGB values. If this is new to you, I would refer you to my P5JS pixel array video, and please leave any questions in the comments if it's confusing. So the red value is my source image pixels at the index plus 0. And I don't need the plus 0 because you add 0 to something, it's the same number. But red is at 0, green is at 1, blue is at 2. So I like to kind of keep my code neat and tidy that way. And then the index in the destination is just, I'll call it index 2, I plus j times the width times 4. I don't need the offset of the source x and source y. Sorry, destination dot pixels index 2 plus 0 equals r. I'm copying over those pixel values. And there's no alpha in what I'm doing, but let's just bring it over as well. And then I'm going to need to update the pixels of the destination. Again, this is just the same as what I did before, but since I'm doing it manually, I'm going to be able to add some code for wraparound in a second. But let's just make sure this actually works. Destination not defined. Image, IJ. Oh, tile image is the destination. Great. This worked, but I have this, but everything looks wrong. So I must have made a mistake somewhere. Let's take a look here. Yeah, there needs to be a parentheses around this whole thing. Oops. Oh, this is a plus. My formula is wrong. I know what the problem is. This W, that is the size of the tile. It will work for this, but remember, this needs to be the width of the source image. There we go. So this is right, but I haven't actually accounted for the wraparound yet. What I need to do is say if the X position of the pixel plus I goes off the edge, go back to the beginning. And I can use the modulo operator for that. I'm going to say PI for the pixel I equals SX plus I modulo the width of the image. So this is pixel I. All right. Not great variable naming going on here. Pixel I would probably be a better choice. When I release the code for this video that you find in the description, I will make sure to rename a lot of the variables with more descriptive language. And then pixel J is SY plus J modulo the height of the image. Now when I run this, we should really see all of the tiles with proper wraparound. Let's stare at this and see if it's right. Again, this would make so much more sense to look at as a 9x9 grid of tiles. One thing that's a little confusing is J is my inner loop. So I'm actually putting the tiles as they are moving, sliding down in the image across. I'd like to actually visually see it the other way. So I'm going to just swap that here in this loop. And this makes it a little easier for me to see. All right. So far, all I have done is look at a source image and iterate every possible 3x3 pixel tile from that source image. The key to wave function collapse, the overlapping model, is not just what are all the possible tiles, but what are all the possible adjacencies of how one tile might appear next to another one. And that's where this word overlapping comes in. For any given tile, I need to build a list of all of the possible tiles that could go to the right of it, up, down, and to the left. And the way that a tile is allowed to be adjacent to another tile is based on its overlap. So let's presume that I have tile A and I have tile B. Tile B is allowed to be positioned next to tile A if its first two, well, I guess I'm saying not just next to it, but to the right of it. Tile B can be to the right of tile A if its first two columns of pixels perfectly overlap with these last two column pixels of tile A. And the same thing would be true for if tile B would be allowed to go to the left of A if these last two columns of pixels overlapped with these first two columns of pixels. And we could do exactly the same for up and down. What this means is I would like my tile object to store a list of allowed adjacencies in addition to just the image of the tile itself. Adjacency is such a hard word to spell. Let's use neighbors. But I have a better idea. Let's make some constants. Uh-oh. I think some of these are built-in variables in P5. I'll worry about that later. I think I can manage to spell adjacencies. Adjacencies is an empty array. It's going to be, I'll make it a J can't, no, I can't do this. I can't spell adjacencies. And then I'm going to initialize empty arrays for right, left, up, and down. So each tile will store its own image as well as a list of all the tiles that are allowed to be to the right, left, up, and down from it. However, I think what I want to store in those arrays is actually the index to the tile image, not the image itself. So let's have each tile know its index. That means when I extract the tiles, I'm putting them into the array, and its index is the current length of that array. Because when I put the first one in there, its index is 0. And then the second one, its index is 1, which is the length of the array before the second one goes in. That should work. So each tile should be able to calculate its adjacencies, calculate neighbors. That will make that a function, and it has to calculate it according to all the other tiles. So for example, now we just need to loop through all the other tiles. And as long as I is not equal to this dot index, right? We know that a tile can't be adjacent to itself. This is not true. It's perfectly fine for a tile to be adjacent to itself if the pixels match up correctly. And later, this extra if statement will not be in the code, as you'll see. I need a function which can compare tile A and tile B according to whether it's overlapping from 4 different directions. So compare tile, this tile's, let's just use the image. This tile's image and tile's index I dot image. I want to compare it to the right. So I'll use that variable and I'll say if they're overlap, if those two tiles are overlapping to the right, then this dot neighbors to the right can store the index to the tile that's overlapping to the right. And actually it would make sense for this function to be inside of the object because the object stores its own image. So I could just say, if this is overlapping this image to the right, then it could go inside of its neighbors. So now I just need a function called overlapping, and it gets another tile, I'll call it other, and it gets a direction. So right now I'm just gonna hard code this. If direction equals right, let's think about how do I need to do this. What I need to do is just check to make sure every pixel is the same in the last two columns of this tile and the first two columns of the other tile. So let's create a Boolean variable called same, and I'm just gonna assume it's the same. And as soon as I find a pixel that's not the same will become false. So what do I do? If it's to the right, I'm looking at I starts at 0, I goes up to 2 pixels. Oh, no, of this tile, I'm actually starting at pixel 1. Again, it'll be nice. There's probably a general purpose way of writing this, but I'm going to hard code some stuff right now. I'm starting at column 1, which is the center column. I'm going all the way to the end, which is 3. And then I need to look at all of the rows. So J just goes from 0 all the way to 3. Now I need to get the pixel location inside of this tile. So the index in this tile is I plus j times 3. Oh dear, some pretty significant issues here. First of all, I forgot to rename that variable I to j. I also forgot a pretty significant thing in the pixel index calculation. I didn't multiply by 4. It will be a while till I fix that, so I just wanted to point that out to you here right now. And then, so the R for this tile is R, this image, dot pixels, index, plus 0. So once again, I'm getting RGB. Now, the other index, which I'll call index 2, is I minus 1, because I'm going from column 1 to 2, and I want to go from, in the other image that I'm checking if it's overlapping, from column 0 to 1. So it's I minus 1 plus j times 3. And I'll call this index, let's call it index A, RGBA, and we'll call this index B. I think that, because that's how I drew it up on the board. I'm comparing tile A to tile B. And then I have RGBB is other image, A, B, B, B. And now all I need to do is find out if any of those colors are not equal. If RA is not equal to RB, or green or blue. See this line 42 there? It's a lovely, beautifully written if statement that is simply checking whether the red, green, and blue values of one pixel are different than the red, green, and blue values of another pixel. This is not the issue at hand right now. There's other mistakes in my code that I need to fix, but I want to highlight this for you because it's correct, and there's no reason why I should ever change that line of code. Same equals false, and honestly, I can just break out of here. I don't need to continue the loop if I find something that's not equal. But if I get through everything, right, if direction equals right, and then I get through all of this stuff, I can just return same. Okay, this looks good. So let's see if this works just for tiles to the right. Something is broken. But before I fix what's broken, let's go back here. Actually, this is silly. I don't need same equals true. As soon as I find something that's not equal, I just return false. And then if I get all the way to the end, then I'm returning true. But I still have some mistake somewhere. All right, I don't need to draw all the tiles anymore because I'm not doing that anymore. So let's take all that out. And I'm using the reserved variable right. So let's not do that. I'll call these T right, T left, T up, and T down. Maybe not the best variable naming. It made sense to me at the time. I think I was thinking T for tile to the right, for example. I don't know, maybe north, south, east, west would be better. What do you think? Let's just draw the first tile. Okay, that is the first tile. What I would like to do now is look at and examine all of the tiles that I have theoretically calculated that can go to the right of it. So after I've extracted all the tiles, I need to call the function calculate neighbors for each tile. Oh, right. This has to be t right. And the other thing that I'm passing in the overlapping function is not the image, but the tile itself. Oh, look at this mistake. The index needs to be passed into the tile object, not it's. I have it after this parentheses, which is somehow pushing both these things into the array or something awful like that. So this needs to go here. Not fixed yet. Let's just try if they're not all equal. It should be the same. Where is it doing some recursion? What? Oh. This .image equals image is causing a problem. For whatever reason, I take this out and there's no error. Why? Hi, I just lost like an hour. For some strange reason, I'm gonna type console log hello here in my setup function, and you see this beautiful hello in the console. But I had a console log of the tiles array. Notice how nothing is in the console. So I went and took a look at the actual browser JavaScript console, and I'm getting some weird stuff where like a maximum call stack size exceeded. So a lot of stuff broke simply because I'm trying to console log this array of objects, and I'm not exactly sure why. Here's the GitHub issue about the problem that's happening here, and you can follow the link in the description to learn more. But I'm just gonna ignore that right now and keep going, because actually I thought my code was broken, everything is working. And what I want to do next is look at and render all of the tiles that can be placed to the right of tile 0 to make sure my neighbor adjacency calculation is working. Let's also add a no loop here. And I'm a little bit afraid to add console logs, but let's try console log tiles index 0. It won't log anything in my tile object. It's the same issue. Relax, Dan. It's okay. Can I look at the neighbor's object? Yes. Okay, great. So you can see there are 31 possible tiles that can be placed to the right. Let's draw them to see if we can see that the pixels match. This is very hard coded. I just want to look at all of the tiles that can be placed adjacent to the right of tile 0. Let's render that image at w, 0, w. And I'm rendering the tile image. Oh, these are index values. Let every index, right? Remember, I'm putting the numbers in that array. So I need to go to tiles that index dot the image. Okay, so that actually makes sense. Great. Okay, w, and I want to put it w times 3. I'm just trying to place it to the right. Okay, so this isn't right because those do not overlap. Let's at least start putting them down. So the first one looks correct. The second one is correct. The third one is correct. Make them a little bit bigger just to see. Oh no, these aren't. The second one isn't even right. Okay, hold on. Ah, look at this. Ah! J needs to be less than 3. J++. Okay, the first one is right. Why is the first one right, but none of the other ones are? So let's figure something out here. Let's render tile 0 and itself twice, okay? Those two tiles, let's just put it further to the right. Okay, console log tiles index 0 overlapping itself. Undefined. I forgot to give it this. True, but they're not overlapping. Hi, I know I'm interrupting, and I want you to keep paying attention. There's an error that I have yet to find that's causing the check as to whether the tiles are overlapping not to work correctly. But keep following also the if statement. It's still right. It's still checking whether the RGB values are not equal to each other, but I moved the not to the outside of the parentheses and then changed all the not equals to equals. Ugh. So let's console log all of the RGB and all of the color values. We should be getting a false. These are not all equal. Let's go back to if any of them are not equal. So I like that better. Shipman, I don't like to talk to myself in the third person, but we've got a serious problem here. You're introducing new errors. You're messing with the if statement. That's not where the actual bug is. You forgot to change one of those ampersands back to an or now that you're putting it back around. And they still have the same thing. Oh, let's take this out. Sorry. I'm just checking overlapping right here. I just want to check overlapping. True. I looked at 6 pixels and they're all the same, all white. That's not correct. So I'm looking at the wrong pixels. Okay, let's look at console log, index A, index B. 1 and 0, 4 and 3, 7 and 6, 2 and 1. How long have I been here? And I forgot the times 4. Oh my goodness, so long. So long have I been here. All right, so finally you found the thing that you really need to find. But you should notice now, look how the auto format added some extra parentheses, and that should be a clue that there's a new error that you introduced in the if statement. False. Those are not overlapping. Now, let's go back and have them all calculate all of their neighbors. Let's look at all of them. Let me get rid of these. And let's see. Is there only one tile that's actually overlapping that one? That would make sense. That's the only one that can go next to it to the right. So this is why I've been asking you to follow that if statement all along. There's a huge mistake still in my code where there's an and where there should be an or. But what you're going to see is the code works. Which tiles are next to which tiles is all correct. That's because the sample image that I'm working with, city.png, only has red, white, and black pixels. The green value and the blue value are always equal when you have red, black, and white pixels. They're either both 0 or they're both 255. So this if statement happens to just work for this one particular image. Only after I finished the recording session for what you're watching right now did I discover this problem. I'm going to come back later in this video and correct it and show you a lot more, but I just want you to be aware of this because I'm going to keep going for quite a while with this mistake in the code, and yet it somehow is working. Let's look at like a different tile. Look at that tile. Those are all the overlapping ones that could go to the right of it. This is now correct. We've got some momentum here. We might get through this. So that was checking to the right. I hate what I'm about to do, but let's check to the left. I'm going to just do these as 4 separate checks. This could definitely be consolidated, but let's just do if direction is to the left, then I'm going to do everything the same. I just keep copying and pasting that same error, so it's in more and more places in the code. But I'm going to start from 0 to 2, and then I'm going to look to I plus 1. Because now I want to know if the first 2 columns of tile A overlap with the last 2 columns of tile B. And then I can do exactly the same for up and down. Except J, I'm going to be looking at 2 rows compared to 2 rows rather than columns. So I will always go from 0 to 3. And so tile A, if it needs to see what could go above it, needs to look at rows 0 and 1 as compared to rows 1 and 2. J plus 1. So this should be for comparing tiles above. And I've got one more to do. T down. I'm going to go from 1 all the way to 3 and then look at compare it to J minus 1. So if we want some visual confirmation that this is working, let's look at the neighbors that are allowed to go to the left of it. None. Well, that shouldn't be right. Oh, well, I need to actually check all of the directions. Now, I've drawn them visually in a weird way because I need tiles that are appearing on the right to be overlapping with the left of the tile that's on its left. But I think you get the idea. This is looking good. Those are all the tiles that can go to the left. Let's just visually look at up and down. This doesn't seem right. These should be oh no, this is right. Look at that. Now, one thing you'll notice is there are redundant tiles, which is fine. As I pan over the image and extract all of the tiles, some of them might actually be the same. Now, I should be keeping track of the frequency of how often they appear in order to use that as a probability for when I start to render them in place. But actually, just by duplicating them multiple times in the array, at some point I'm going to be picking things randomly to go next based on what can go there. And if it's there more often, those probabilities will work themselves out. Let's look at down. Right. These are all, look at these. All of the tiles to the right of this tile on the left have the same first two rows as the bottom two rows of that tile on the left. I want to say that we've done the hard part, but I'm not so sure about that. Everything that I'm doing to draw in the canvas was just purely for debugging's sake. I have now what I need, which is a collection of every single tile that appears in the original image, as well as lists of all of the valid tiles that are allowed to be placed adjacent to those tiles, to the right, the left, up, and down. And this is where it's time to play our own special generative art version of Sudoku again. What I have is my P5 canvas. What I want to do is fill the P5 canvas with those tiles. When the sketch starts, every single cell inside of the canvas could have any one of the 81 possible tiles rendered into it. So what do? I just pick a random cell and choose a tile. Let's say I place tile number 3 in it. Well, that means the up neighbor to the up, neighbor to the right, to the bottom, to the left, all of these have a reduced number of possible tiles because that tile 3 has a list of valid neighbors to the right, left, up, and down. This means what I can do next is, because those cells have a reduced possible set of tiles, I could go to one of them and pick one possibility, and then go to their neighbors, and so on and so forth. I want to propagate out, reducing the entropy of all of the cells and see if I can magically somehow fit a puzzle together where all of the tiles are next to tiles they're allowed to be next to based on the adjacency rules. Let's start implementing this in the code. This is where a lot of the code that I went through and developed in the previous video will actually be the same. Hopefully I could get through it a little bit faster here. So I need something called a grid, which would essentially be an array to keep track of all of the possible cells. I'm also going to want to have a cell class. This is different than the tile class. The tile is the actual image that can be placed inside of a cell. So let's create another JavaScript file. When it begins, the options of what could be placed in the cell is everything. I'll just pass in that tiles array because then it can pull from the tiles array and add. That's a very silly way to put a whole bunch of numbers into an array, but it will do. So a cell object, all it holds is the array of all the possible tiles that could go there. I also want to have a Boolean variable so that I can check whether it's been collapsed or not. So when it starts, it has not been collapsed. So maybe I'll make the grid. Should I make the grid a two-dimensional array? It doesn't actually matter. I'm going to keep I think in the previous version, it was a one-dimensional array, so I'm going to keep that. But for every possible spot, push a new cell based on the tiles. Then in draw, what I want to do is render what's there. I guess the cell could kind of know where it is. That could be helpful just for the drawing purpose. So let's write a function inside of the cell class that draws itself. And for now, let's just draw it as a square. And let's have the cell know its XY position and its size maybe. So all it is right now is I'm gonna draw an empty square at its XY position. And in the main sketch, when I create the cells, I need to say I times W, J times W. So I'm gonna need this variable up here as well. And let's run this. And I also need to give it W. And I did that. I made the same mistake. These are not meant to be pushed into the array. They're part of how I'm constructing the object. So the parentheses need to be in the right place. Cell is not defined. Well, that should do the trick. W is not defined. This dot. There we go. So we can see all of the cells and they're empty. Let's change it to 20 by 20. So I'm going to have a little bit of an easier time kind of seeing as we're building this up. Wave function collapse. That's what we're here for. Step 1, pick one random cell. Now, actually, if you remember from the previous version of this that I made, the idea is to sort all of the cells by their entropy and pick a cell with the least amount of entropy. That's actually quite important. So let's bake that in. Dare I get my code from the previous one? I think I should. Okay, look at this. Make a copy of it, filter out all the cells that have been collapsed, then sort by the length of the options, keep only the lowest, the ones with the fewest options, and then pick a random one. Oh, this is great. We can actually just use all of this. Isn't that nice? Sometimes a part 2 really works out. So I might have named things differently, so let's see. We're making a copy of the grid. Again, filtering any that are collapsed. We're done if there's nothing left, if everything's been collapsed. Sort by the least entropy. Now, technically there is an actual formula for entropy based on the number of options, but I'm gonna collapse my own brain here and oversimplify by just saying the number of options is the measure of entropy. And then again, picking randomly from the ones with the least entropy and collapsing it and picking a cell. Oh, okay. So if I've picked one, hold on. Let's go back to the cell class. And I'm going to say, if this is collapsed, if it's collapsed, I'm going to draw something. Otherwise, then just do this blank square. If it is collapsed, what do I want to do? Well, the image is the only option that's left. Tiles is a global variable. I'm just going to access the global variable right now. So the tile index is this dot options index 0, because if it's collapsed, there should only be one thing left. And then the image is from that global variable tiles, tile index. And then I should be able to render that image, call that global render image function, where at this dot x, this dot y, and with some amount of space, let's say this dot w divided by 3. I think that's because I made a certain amount of space for the tile, and if it's 3 by 3, I need the pixels to be the width divided by 3. Let's just see what we get here. Okay, did we actually collapse something? Let's put this into a function, because I have no loop in here. Let's actually write a separate function called wave function collapse, or WFC. So if I call that in setup, I should have one cell. Image load pixels is not a function. So where am I calling that render image? I'm calling it from the cell, and the image is tiles tile index dot image. Put my auto refresh back on. There we go. Look at that. That's the random one that I picked. Now, why is it always picking the same tile? That doesn't seem right. Let's go take a look at why that's happening. Oh, of course. Somehow, I must have missed copying a line of code, but I need this cell, options, to equal only the thing that I picked. So I have to override it. Okay, there we go. So now it's always going to pick a random option. And again, I think it's kind of hard to see, so let's make it 10 by 10. There we go. So now it's always going to pick one. I'm starting with one and putting it in its spot. Beautiful. Mwah. Just for fun, let's take off no loop, and I'm going to call wave function collapse from draw. Look, now, one at a time, it's picking a tile for every single cell, and eventually it's going to run out. But this is no good. What I need to do is not just continue to pick random tiles, but because I happen to pick this tile in this spot, that means I reduce the possibilities to the right, left, up, and down, and I'm going to then go and look for the tile that has the least entropy and pick that one next based on what's available. So let's write a function called reduce the cell, reduce entropy of the grid based on a cell. So this could go in the util, but I'm kind of now doing the wave function collapse algorithm in the main sketch file. So let's write a new function called reduce entropy. And I'm just going to absurdly name the arguments the same variable names, but that should work for me. So the first thing I need to do is look at the cell's index. The problem is the cell doesn't know its index. So let's give the cells their index. So another thing I have to tell the cell is where it is inside of the grid when I create it. So here we're creating the cells, and I'm doing the same exact thing here. So let's make a counter. I could use the length of the array, but I think this is actually just a little bit more logical to me. The counter will go up. I will pass that in for every cell to know its index. And I'm realizing that in order for the counting to match up properly, I'm going to have the columns be in the inner loop, which is the proper way to do it, but I just never seem to do it that way. So I'm going to put this for loop on the inside here. And let's just double check this. Again, if I look at the grid, we can see this is the grid. Every cell has an X and Y position. It has a width. It has its index into the array, as well as what is a possible option. And you can see there are 81 possibilities for every cell at the beginning. So the index, I'm going to reduce the entropy, is the cell's index, which means I is the index modulo the dimensions, and the J, its row, is the index divided by the number of dimensions. So I'm taking its one-dimensional index. I'm doing the opposite of that pixel calculation where I have the column and row and I find the one-dimensional index. Now I have the one-dimensional index and I'm finding the column and row. Why? Because first I need to look to the right. What cell is to the right? What should I call this? I'll call it neighbor's I is I plus 1. Now, as long as that is less than the dimensions, I'm okay. I don't need to reduce the entropy of a cell to the right if it's off the edge. So as long as it is less than the dimensions, then I need to look at what are the valid options to the right. The cell to the right is in the grid at ni plus j times dimension. That is now taking the new column, the same row, getting its cell. So I need to somehow figure out what that right cell's new valid options should be. In order to do that, I need to look at, well, I know that the cell, in this case, eventually I'm gonna have to make this probably recursive, and I have to consider all the valid options based on more than one possible option. So maybe I should anticipate that right now. But essentially, I need to look at all of the possible options of the current cell that's reducing the entropy of the cell to the right. So I'm going to say for let option of cell.options, and then the valid options from there are, I'm going to go back to the tiles. That particular, the option is the index. I should say index. All of the possible, am I using index already? I am. So I think I'll keep option. Remember, cell.options is a list of all of the possible indices of valid tiles. So if I look at a particular tile and then look at its neighbors to the right, those are the valid options. But I'm going to be doing that for more than one cell. So I actually need to start with an empty array. And then what I'm doing is I'm concatenating it. Valid options equals valid options dot concat with the new options. This is quite long. And just for right now, I'm going to move this over here so we can see it. These are all the valid options of anything that could go to the right. However, I now need to also, those are all the, so on the one hand, I could just say right cell dot options equals valid options. We could just try that as a starting point. And in fact, I'm kind of curious to let it run with just that and see what happens. Yeah, okay. So it's very hard to see what's going on. Are they overlapping correctly? Because one of the things that I haven't revealed to you is we're not actually drawing the whole tile. The reason why we're trying to figure out if tiles are overlapping is we just want one pixel from the tile. So actually the proper way to look at this is under util, I need a new function that's not render image, but I'll call it render, I'm going to call it render cell. And what we're actually doing is just looking at the center pixel. And I don't need this extra, I'm going to take out this square right now. But basically, I'm looking for I equals image.width divided by 3. J equals, not by 3, by 2. And flooring it. I mean, I know it's 1. I'm like, half the time I'm hard coding the 3, and the other times I'm not, but let's not hard code it. I'm looking for that center pixel, and then I need to draw the center pixel at the correct spot, which is just actually, there's only one pixel, so it's X and Y at W times 3. Let me just think for a second. Can I do this better? First of all, this should be J. This is the same function, but instead of drawing it as a 3x3 grid, I just want to draw the center pixel across that whole space. This is me drawing it based on W. Let's try that. So let's go to, where was I drawing that? I'm drawing that in the main draw loop, grid.show. So the cell.show, I'm now saying render cell, the image, and I don't need to divide by 3 anymore. Perfect. I had that in there already. Okay. There we go. Okay. So this is what it's ultimately going to look like. Let's go back now to making the dimension a little bit larger. So what we should be seeing is just cells that are propagating and being placed to the right correctly. So I'm not seeing the whole image, obviously, but I'm seeing cells that are overlapping properly to the right. So one of the things that's incorrect about this is assuming the right cell has a limited set of options that it's somehow gotten to from before, it should only keep the ones that are also in the valid options, but not just overwrite itself with all the valid options. In this case, it probably didn't matter, but I think I should correct that here. So how do I do that? Basically, I want to filter that array. I could use the filter function. I want to filter it by things that the valid options includes. Filter. So filter is a higher order array function. I have a bunch of videos on those where I'm going to look at a given element and I'm only going to keep that element, and I'm using the arrow syntax. I've just gone all in here. I'm going to use the arrow syntax to create this like very simplified version of this function. I'm filtering it. Every element should be kept if valid options includes that element. Let me run this. Interesting. It's doing something different. Do I need to? I think I need to set. I think that is a function that creates a new array. No. Oh, right cell dot options. There it is for you, right? The right cell options is a filtered array of its current options if that option is in the new valid options. There we go. We can see it's kind of propagating now to the right. Beautiful. Now, I essentially need to reproduce this exact algorithm for the left. Left. So ni is I minus 1. I need to check to make sure it is greater than or equal to 0. This is now technically the left cell, and I'm looking to the left. left cell, left cell. Anything else I need to change? Think that's right. You know what I should just do? I don't need this variable. I'm just checking if I plus 1, and this is I plus 1. I'm just checking if I minus 1, and this is I minus 1. That's a little bit nicer. Let's run this. We should see things going off to the right and left now. There we go. See, look, I'm only propagating to the right and left, so things are tiling in their correct spots, but not relative to up and down. So now I should be able to do up and down. Let's start with down is plus 1. So I'm saying if this is down, j plus 1, and this becomes j plus 1 here. This is the down cell. Down cell options are filtered, and I'm looking down. Okay. Okay, so it broke because it ran into a conflict. But don't worry, look, don't you see that kind of looks like that original image is starting to exist there. Oh, this is very exciting. Okay, let's do up. J minus 1 is greater than or equal to 0. This is just the reverse. Then that is the upsell. I'm upselling you on something by my nature of codebook. No, maybe you don't. If you're still watching this, then you've done enough. Trust me, it's all good. T up, upsell, upsell, upsell. Okay, it immediately broke, like kind of running into a conflict almost immediately. So why is this happening? I am a measly little cell inside of the bigger P5 canvas. And I got picked to be a particular pixel color, which means I've reduced the options for the pixel colors to the right, above, to the left, and down. But if this one is reduced and it only has a certain number of possibilities, then only things that can go to the right of those possibilities should be allowed, which means I should reduce these as well, and so on and so forth. And this can be done with recursion. So if I call reduce entropy on this cell to reduce the possibilities for these 4, then while I'm doing that, I would also recursively call reduce entropy on these 4 to reduce their neighbors, and so on and so forth. Let's try adding that into the code and see if that reduces, that gets it to run a bit longer and like make fewer mistakes. The idea is I don't want it to find a spot where there's nothing left that could go there. And it really is as simple as now saying reduce entropy on the right cell. However, I've got to think about this because I could get really stuck in an infinite recursive loop here. So I need to call reduce entropy. I need to pass the grid and that particular cell. And then we'll do the same for the left cell and the same for the down cell. And the same for the up cell. Maximum call stack size succeeded. So that error is because I am recursively checking a cell to the right, which then asks to check recursively back to the cell to the left, and which then asks to check the cell to the right. So I think what I also need to do now is every cell needs a Boolean variable called checked, which would start as false. And then the first thing that I would do if I'm reducing the entropy is I would say, hey, has this cell been checked already? If so, just return. Otherwise, cell.checked equals true. Oh, but then the cells every time through draw at the beginning of the wave function collapse algorithm, all the checked values need to get set back to false. I could do that while I'm drawing them. Grid index I checked equals false. So I'm going to draw them, set all the check to false, and then let's see what happens here. Cannot read properties of undefined. No, down is j plus 1, and up is j minus 1. How's that? Oh! I left a plus 1 there! I'm checking j minus 1, but then I looked at the cell below. There we go. Look at that beautiful... I don't know what I was doing all along, but somehow we got wave function to work. Oh, it broke. It didn't find, it can break still. It can get stuck, but that's fine. I just want to fix some things. Tile util. When I'm rendering the cell, let's not give it a stroke. This is where it's doing, let's just make this very, very light and thin. Oh, do I not have the background drawing? I don't have background 0. No wonder it's looking so strange. Okay, this is more like what I expected it to look like. It's running quite slow. So I am letting the recursion just propagate out as much as it possibly wants. But the truth of the matter is, I don't actually need to recursively keep reducing all the options as far as I could possibly go. I should be able to get this to work just fine by keeping track of a depth of recursion. So let's add that in, and it's still getting stuck. But let's fix the recursion to have a depth. So I'm gonna add a depth variable, and when I first call reduce entropy, I'm gonna give it 0. Then every time I call it again, I'm gonna say depth plus 1. So as I recursively call reduce entropy, I'm always increasing that number by 1. And then at the very beginning here, I can also say like, hey, you know what? If depth is greater than 2, return. So that's just a very, very small depth. Let's see what happens here. You can see it's already running much, much faster. I want it to at least finish once. This should be grid copy. Grid copy.length equals 0. That means everything has finished. Oh. It completed one. It is possible. So I just have to get lucky. Backtracking would be the thing to do. If it gets stuck, I track back. So where do I need to put something in if it fails? If a cell has no more options, I know what to do. In the cell, I'm going through all of them here. So if for some reason, if not cell.options, if it has nothing, then, and normally I would draw it red, but this pattern has red in it. This dot options. Let's just make it blue. Let's see if I can just draw something blue if it runs out of options. This dot options dot length equals 0. There we go. Okay. Fill. I want to fill it. So if it gets stuck, it's going to draw all the cells where it got stuck with blue. Maybe this one's going to work. Okay, great. So for whatever reason, it got stuck with these over here. I think there's something else that's wrong here. By the way, I switched it to this flower pattern because I was curious just to see it run with something else. And if this left cell that I'm about to examine was collapsed, I shouldn't be like figuring out what its options are. So I should actually be saying something like, as long as left cell, as long as it exists and left cell is not collapsed, then do all of this. So I need to do that for all of them. Same thing for the down cell. Make sure it's not collapsed. Same thing for the up cell. And then, of course, the right cell, which is the one that I started with. Let's see what happens when I run it with this. And it's working. Okay, this was a total mess. Yeah, but I'm gonna stop now. So I had to wrap up that session kind of in a hurry. I think I was late to pick up my kids from school. And as soon as I got home and was able to open up the code again, I was very excited to try it with other sample images that are in that original wave function collapse GitHub repo. So I went through and I opened up this file called water.png, and the code didn't work at all. It just was broken, stuck, made nothing. This is because water.png has blue pixels in it. Went to the Coding Train Discord to try to talk it through and figure out what was wrong, and only then did I finally discover the faulty if statement and correct it. Now, I wasn't recording myself at that time, but I did come back the next day to fix the error and do another session improving the code, which you're about to see right now. 1 day later. Well, didn't really take my own advice yesterday, which is that sometimes when you're working on something for a very long period of time and you're just getting stuck, it's a healthy and productive thing to do, to take a break, to put it aside, get some sleep, come back fresh the next day. Here I am. And of course, I found where the mistake that was getting me very stuck was. So I want to fix that mistake. Let's see if we can refactor, optimize, reorganize some of the code. Maybe I can take a deep breath and walk through the algorithm a bit more with some additional explanation to maybe make this video somehow make more sense. And then add a few more features, talk about some exercises I'll leave to you as the viewer, and call it a day, a second day, that is. Here is the code running, loading as the source image, the sample water pattern. What you're seeing in the canvas looks nothing like what's actually in that pattern and is running incredibly slow. I don't know when this happened. Oh, I do. I know when it happened. But sometime the code got changed. The correct logic for me to compare if two colors are different is to check whether the red values are not equal, or the green values, or the blue values. Let's run the sketch again. There we go. This looks much more like the correct wave function collapse output for that particular seed image. But it does bring up a central problem to the way that I've been developing this, which is anywhere in the code where I need to apply a particular piece of logic to all of the neighbors, I have huge sections of redundant copy-pasted code. That was just kind of the way I was doing it in my raw, unfiltered coding challenge style. But this video is so long anyway, let's take a minute to look at how I might adjust this section to pull out repeated code and refactor it into a separate function. The central idea is I have 2 pixels from 2 images. I need to check if they're not equal. That you can find here in this big block of code. Let's take that block of code and put it into a separate function. If, what should I call this function? Different color of what? This dot image, index A, other dot image, index B, return false. And I need one more parentheses there. Now, again, there's more redundant code that I might be able to refactor this even further without having separate if statements for right, left, up, and down, but this is a good start. This means I just need to write this function. Let's put it at the bottom. Function different color, image 1, we'll call it image A, image B, index A, index B. And presumably, the indices have to be calculated up here. So I'm calculating both indices and then calling the function with the indices and the images. And now, actually, this function, if they're different, should return true. And actually, I can just say, return the result of this Boolean expression. And by the way, I do not need to load the pixels. This is something I'll get to more in a minute. I want to make sure I am loading the pixels of the tiles and images I'm using the minimum number of times, because that is a slow operation. So now, in the left check, I can do exactly the same thing, calculate index A and B. Actually, I should check to make sure this is working. Oh, okay, what's the mistake? Cannot read properties undefined reading pixels. The arguments this is an arbitrary decision. Do I want image A, image B, index A, index B, or image A, index A, image B, index B? I wrote it the other way. So let's put it back this way. And of course now, in the function, which is a generic function pulled out, this and other are no longer relevant. So image A. Everything is working as expected. That's good. I can continue to refactor the other 2 sections. Let's run one more time to check. Looking good. Again, this is just a small step in the direction of refactoring redundant code. I expect there's more that could be done here. Look at what's repeated. I'll leave that to you as an exercise. Let me know what you would do in the comments. Let's refactor one more spot in the function where I am reducing the entropy recursively of neighboring cells. I have a ton of redundant code for the right cell, the left cell, the down cell, and the up cell. Let's call this function check options. The idea of what I'm doing is I'm checking to make a list of the options for the right cell, based on the direction to the right. And I think that's it. All of this code can then be refactored into this other function called check options. Let's write check options, neighbor, and direction. So right cell becomes the generic neighbor. If the neighbor exists and is not collapsed, this is the direction, and this is that neighbor, this is that neighbor, and I think we're good. This is checking the option of, it's really setting the options of a neighbor from a given direction. But there's something else here. I need to get the valid options from a current cell that's applying it to that neighbor. That's here in this variable cell. So that has to be passed in as well. Check the options of this cell to the right cell in the right direction. And then afterwards, reduce the entropy. Still working. So I believe I can just now put this here. Oh, the reduce entropy is inside of this if statement. I don't need to reduce the entropy recursively if it is collapsed. So that's interesting. Let's return a Boolean. I'm going to call it checked. I'm going to return that Boolean. And if it's checked, then go ahead and reduce the entropy. So this function should return true, otherwise return false. If this stuff doesn't execute, don't bother reducing the entropy recursively. Still working. And now we can take all this out and put this in for the left cell in the left direction. Let's do this to the last two. Probably still some opportunity to think about refactoring this further, but I like this much better than what I started with. See, a fresh day, a fresh approach to the code. Now, amazingly, it's not getting stuck. This particular pattern seems to find a solution with a max recursion depth of 3. Let's make this a variable, call it max depth. And I'm going to just make it 1 to see if we can have it get stuck. Maybe this is an easier pattern where it's less apt to get stuck. Oh, there we go. It got stuck. I did get an error here. So what I would like for it to do is stop but not produce an error. And presumably, I could also implement a feature where maybe it would restart, so it keeps going until it finishes. When you have a project like this one that fails sporadically at different times, only sometimes, it can be really helpful to set a random seed in setup so that you can consistently produce the same exact pattern over and over again. So let me try adding random seed. I'll just pick arbitrarily 99, run it. So this was a perfect one because it failed very quickly. And if I run it again, there we go. So it's telling me that the error is in line 136, which is down here. This is actually quite nice. The error is happening in the check options function. So it's really great that I broke that out because otherwise the error would happen in different places in the code that was repeated. But it's happening because there are no options of that particular cell, which stems from the fact that if the cell has no options and I'm trying to collapse it, that pick will be undefined. So I think what I need to say is here, if not pick, if there's nothing picked, then console log ran into a conflict. Let's just say return and also no loop. I think that should stop it from running at all anymore. It'll never get to these next lines of code, and it will print out this ran into a conflict message. Ran out of options, ran into a conflict. Where did I have my other console log for my chaotic debugging yesterday? I'm doing it inside of the reduce entropy function. Interesting. Do I need that anymore? Let's take it out and see what happens. Okay, even better. I'll leave this to you as an exercise. I'll also provide a solution, which I'll show you on the screen here, for how you might restart the algorithm if it reaches a conflict. All right, let's take out the random seed. Let's increase the max depth to 5, and hopefully that should be enough for it to have a good chance of solving. Oh, it ran into a conflict. Is there a 0 option? Hold on. This if not pick is a huge problem, because if the actual legitimate option is a 0, that will evaluate to false. So this actually has to say if pick is equal to undefined. I'm going to let this finish. Beautiful. Let's try it with the city image. Oh, it ran into a conflict, but let's try again. And also, I don't need this console log anymore. So if you're running into a lot of conflicts, I believe by increasing the maximum depth, allowing the recursion to go even further, that will reduce the risk of conflicts coming up. Let's try doubling it to 10. It's a performance trade-off, of course. The higher the depth, and it got a conflict again, the longer it will take to perform the recursion. I just want to address something you might be wondering about. Look at those red rectangles that have huge blank spaces in them. Shouldn't those all just be red? Shouldn't those have the lowest entropy? The only pixel that could go there could be red. Well, I just want to remind you again that there are actually many tiles that are the same. So the system thinks there are 9 possible tiles that could go in there because there are 9 tiles extracted that all had red pixels. You're going to see shortly how this can be addressed in different ways, but I just wanted to point that out now in case you're wondering. Now, it is running a bit slow. I think there are probably lots of things we could do to optimize, but the first thing I want to do is make sure I'm not unnecessarily loading pixels many extra times. Let's search for everywhere I'm loading pixels. Nowhere in main. What about in the cell? Nowhere in the cell, that's good. Aha! When I'm rendering the image, I'm loading the pixels. This shouldn't be necessary because the image hasn't changed since the first time it was created. Same thing, rendering cell, let's remove that. Copy tile. I do not need to load the source pixels. That's what I'm copying from, that's already been loaded, but the destination is a new image, so that needs to stay with load pixels and update pixels. So extract tiles is where the pixels get loaded for the original source image. And in the tile class, that's where the pixels are loaded for every new tile that's made. This also happens just during the setup. So let's run it again. We'll see if it looks like it's running faster. Yeah, this looks a little faster to me. Hard to tell for sure. Maybe it's just the feeling of it faster. Now let's try it with a higher degree of difficulty image, a more complex image, the one that you'll see often used as a demonstration of the algorithm, this image of flowers. I'm going to leave the max depth at 20. Let's see what happens. Well, this one got stuck, and it also was running quite a bit slower. This is simply due to the larger number of tiles and possibilities that just increases the amount of computation across all parts of the algorithm. Let's increase the depth to 40 and run it again. Oh no, it got stuck. I thought this one was really going to finish. Didn't get to finish the cube. I got to move on, but I'll show you a few examples of flowers, images that did actually finish. Let's change the max depth just back to 5. You can see how much faster it is with a lower max depth. Let's go back to the water. I'd like to show you something additional about how the wave function collapse output is typically rendered. Look at the show function. If there's no options left, that's a conflict and I'm drawing a pink square. If it's collapsed, then I'm drawing the center pixel of that particular tile. Otherwise, I'm just drawing a plain empty square. What if I were instead to look at all of the options that are possible for that cell and calculate the average color and draw that? So I need to add up all of the red, green, and blue pixel colors. Get the image tile associated with each one of those options. Then the pixel index is the center pixel, which is 1, 1. Okay, that's a really bad hard coding. Maybe I'll change that before I release this code. Well, that's pixel 5. I think we could do this. These are the hard-coded indices of the red, green, and blue values of that center pixel of a 3x3 tile. Divide by the total number of options. And then fill that square with the red, green, and blue values. All right, let's try running this. This doesn't actually look right to me. Oh, it's pixels. I'm like, this doesn't look right. It's pixels 4, 5, and 6. 1 plus 1 times 3 is 4, not 5. Oh no, I also forgot to multiply by 4. So the correct index is 1 plus 1 times 3 times 4, because there's the red, green, blue, and alpha values. I programmed for too many years in processing in Java where you didn't need to multiply by 4. So that is 16, 17, 18. Let's look at this one more time. Okay, now this should really be correct in terms of the average color. Let's take a look at the city pattern. Notice you don't see those blank spaces anymore. This is because the average pixel color for 9 identical red tiles is red. And let's look at the flowers. So there's a pretty significant issue that I have going on here. And let's see if I can bring this into focus by rendering one more piece of data. And just for the sake of argument, I'm going to change the dimension back down to 20. And what I'm doing here is I'm also drawing into the cell the number of options that are left. Let me increase the depth for a minute so we can see this. And I'm going to type in no loop. All right, what's going on here? Let's zoom all the way in. By looking at this image, we can note a couple things. One is, look all the way at the top left corner, there are 360 possible tiles. But remember, when I am extracting the tiles from the original source image, if there are 2 tiles in different parts of the image that are identical, the system thinks of those as 2 different options. This is good because it weights the probability of what's going to be chosen by pixel patterns that appear more often in the image. However, it can result in a lot of extra computation. Look at this collection of 82 possibilities for those 3 pixels. Clearly, those have to end up being blue. There's a tile that's being repeated many, many, many times. An optimization for this algorithm would be to keep a separate frequency count of repeated tiles and calculate the entropy according to a function of the number of options and the relative frequency of those options. Let's set this running again. Isn't it satisfying to watch all the numbers collapse down and see the final image? While I'm on the subject of the total number of tiles, there's something else that could be applied here. The water pattern is a really nice example of this. What if I told you that this additional image that I'm now showing you on the screen was also generated by the same source image that's generating the pattern you see in the P5 canvas? How was that done? Well, what if you took that original source image and turned it on its side and also extracted tiles from a rotated version of the image, and then flipped it upside down and flip mirrored it? You can take any source image and reflect and rotate it any number of times to extract more tiles. This is what the result looks like with that flower pattern. The city image, by the way, that source image looks the same no matter how you rotate it or flip it. This is what the code looks like for doing those rotations and reflections, and I'll make sure I include an example of that along with this video as well. So now it's really up to you. There are many more sample images on the original Wave Function Collapse GitHub repo that you could try. You could make your own. You could generate your own. I don't know. Please take my code. Hopefully, if I can get my act together, I might even be able to optimize it further. I'm already including with this video several performance optimizations. One is the deduplication of tiles, keeping track of a frequency counter instead of many versions of the same tiles polluting the system significantly improves the performance. Another improvement is collapsing any tiles that just have one option left. The version that I finished up with here only collapses one cell per cycle through draw. But there's no reason why I couldn't check through and see if there are a lot of cells that only have one option left, just collapse those. I could also optimize the algorithm I'm using to find the lowest entropy tiles. Currently, I'm sorting the array of tiles by their entropy, and there's no reason to do that. I could actually just go through the entire list one at a time and find all the ones that have the lowest entropy. I don't know why I didn't think of that when I made this video, even the previous wave function collapse part 1 video. And then finally, I could optimize the drawing. In the code that I wrote in this video, I'm drawing every cell, every frame, all the time. But technically speaking, I only need to draw the cells that have changed since the last cycle through draw. I would love to go through some of these optimizations, in particular, the frequency counter and entropy calculation. It involves a lot of kind of fun code stuff. For example, in order to figure out if two tiles are identical, what I actually did was base 64 encode the pixels into a string and then use that as the key to a JavaScript object in a dictionary-like way. And then I imagine there are other optimizations that people watching this video will suggest. And I wouldn't be surprised if I've made a lot of significant mistakes or gotten things wrong. One thing that I didn't do is actually go and look at the original code in the GitHub repo and kind of compare it with what I did. So maybe some enterprising viewers will do that and provide some interesting suggestions to me. So I do intend to come back and do a part 3. Maybe it'll be a live stream, maybe it'll be a video upload. I'm not really sure, but yeah. Oh, this is not the end because I'm going to say a few more things. Take a look at the video description and the associated Coding Train webpage, which will have any additional information for you about that. Come and join the Discord to chat about it. Share your wave function collapse projects in the Passenger Showcase, and I'll see you next time on the Coding Train.